Hello everyone. Today, me, Penny, and my teammate Fan An, Caitlin, Gwen, and Chunlok will be presenting a mathematical problem involving related rates in a real-life industrial situation. Our topic is the rate of change of water depth in a funnel. The content part will be introduction, sub-question A, sub-question B, and a real-life explanation. Our question is about a local company which has designed a conical water funnel for industrial application. The funnel has a circular base with a radius of 10 cm and a height of 20 cm. The funnel is placed with its tips pointing downwards. During testing, water is poured into a funnel at a constant rate of 4 pi cubic centimeter per second. As part of the product development process, our team was asked to analyze how quickly the depth of water inside the funnel increases as it is filled up. So now, there are two things we need to be calculating. The first one is the rate of change in depth when water reaches 5 cm. And the second thing we need to calculate is the rate of increase in depth after 4.5 seconds of pouring. To solve this, we'll be using the formula for the volume of a cone, and we also be using calculus techniques such as differentiation and chain rule. So now let's move on to see how we approach this problem step by step. I'll pass this to my teammate.
Hi, my name is Lan An, and I will be presenting sub-question A, steps 1 through 4. This question is to calculate the rate at which the depth of water is increasing in the funnel when the current depth of water is 5 cm. The first thing we need to do is find the formula for volume of a cone, which is 1 over 3 pi r squared h. Next, we compare the similar triangles, where 10 cm is the radius of the funnel over 20 cm, which is the height of the funnel, equals to r over h, which is the radius and height of the water in the funnel. Next, we have to express r in terms of h, which means making radius the subject of the equation. Next, we take the formula and eliminate r by substituting it with the equation we found earlier and simplifying it to get our new equation.
Hi, my name is Caitlin, and I'll be continuing on from step 4 of where we have found the simplified volume where there are only two variables of V and H left. So as water is poured into the cone, volume increases, and when volume increases, the height increases. To relate these two concepts, we can differentiate V with respect to H. To do this differentiation, we need to use the power rule. And once simplified, we can form a chain rule, as volume, time, and height are all related to one another in this question. dV over dt is the rate of change, dV over dH is the volume to height rate, and dH over dt is the rate of height increase. Now, from the question, we know that dV over dt is 4 pi, and we have previously found dV over dH. But what is dH over dt? So, to find dH over dt, we have to substitute the values and equations that we first know. So we substitute 4 pi and the equation of dV over dH. Now we can isolate dH over dt and form a new equation. So to solve for dH over dt, we need the value of H. And the value of H from the question was given as 5 centimeters. So we substitute this value of 5 to get our rate at which the depth of water increases, which is 0.64 centimeters per second.
Hi, my name is Ishan, and I'll be doing sub-question B. The question for this question is determine the rate of increase in the depth of water in the funnel 4.5 seconds after the pouring has started. So, in order to do this question, the first step is to find the new volume of water poured in after 4.5 seconds. So we have to do V equals to 4 pi times 4.5. We can get this equation when we calculate the volume at 4.5 seconds using 1 second equals to 4 pi. So that's how we get that equation. So the answer for step 1 will be 18 pi. For step 2 is to find the new height. We will be using the new V equation with the old V equation from part A, which is pi over 12 h cubed. So 18 pi will be equals to pi over 12 h cubed, which will be giving us h equals to 6. Now the last part, which is step 3, we will substitute the new h into the equation. This equation can be found in part A, which is dh dt equals to 16 over h squared. So we will now put our new h, which is 6, into the equation, which will be giving us dh dt equals to 0.44 cm per second. So this will be our final answer for this question. Thank you.
So, in solving this problem, several assumptions are made to make the calculation simpler. The first is that the water is being poured at a constant rate. The question assumes that the flow rate is exactly 4 pi cm cubed per second, with no variation during the filling process. The second is that the water surface is always level, where the water level is perfectly horizontal and fills uniformly the entire time. Next, it is assumed that the funnel is a geometrically perfect cone, with a fixed radius of 10 cm and a fixed height of 20 cm. Finally, it is assumed that there are no outside factors, that things like evaporation, leakages, spilling, and temperature will not affect the flow rate.
Hello guys, I'm Chunglok, and now it's my turn to continue with our presentation. I believe my friend has clearly explained the main question, so now I would like to share some real-life example to understand it better. The mathematical concept of studying the rate of filling a conical funnel with water has numerous helpful real-life applications in various industries. Such calculations are important in industrial and chemical engineering in the filling of liquid products such as oils, detergents, or chemicals by pouring in the container and in an automated filling system. Knowing the speed at which level of the liquid rise enables such system not to spill and pack each bottle or tank to the appropriate amount. Likewise, in factories where mixing or storage of chemicals are applied by using conical tanks, this form of calculation enables better management of liquid level to be managed. In pharmaceutical and food industry, there must be conical funnels during bottling process like sauce or milk, monitoring at an accurate rate in which the liquid level increase allows the consistency to be checked on the health and safety of the medicine being produced all from the same container. Similarly, beverage industry has such system to ensure that all juice boxes or bottles are filled to the same level where there is minimum wastage and complaint by the customer. Even in daily life, the principle from this problem can be applied. As an example, consider pouring liquids using a kitchen funnel into a narrow bottle. Then we frequently see that the rate of flow and the behavior varies with funnel shape. Knowledge of this process can help avoid waste of products in bottling of perfume or essential oils in both small and big perfume or essential oil business. Moreover, knowledge of this process enhances accuracy. In scientific research, understanding how fluid levels change in conical containers is especially important. In chemistry laboratory, tasks with titration can be performed using burettes or funnels to measure certain volume of liquid product with precision. The correct determination of the rate at which the liquid level change is very important to the chemical reaction within known and maintainable condition, which is important to get a varied result. In conclusion, the mathematical concept that is applied in all these cases are not only beneficial in monitoring in real-life activities, but also simulation, construction, and testing of the system prior to the construction. The safety is increased, the accuracy is high, reduce waste, and efficient use of the resources. Thanks for your listening.